Hi, in this video we will learn about a mathematical constant called Euler's number, and then we'll see that we call the exponential function in that base the natural exponential function. The importance of the natural exponential function will be discussed later in the course, especially when we do the derivatives and integral of functions. Okay, so let me start. What is a mathematical constant? Well, these are constants which appear in math, and they have some mathematical importance. Well, the most famous of them that you know is the number pi, 3.14 dot dot dot. So this number is a mathematical constant, but the number that we are going to introduce is a different number. The Euler's number, well, denoted by E. Well, see the number E, the Euler starts with E, is an irrational number which approximately given by, well, approximately it's 2.71828184 continues. Being irrational means that no one can give you finitely many digits and say this is the number E. It never stops, and there is no good pattern that I can tell you, follow this, you will find all the digits. When you see this, first of all, you don't need to remember all the digits. So just keep in mind two first digits. So E is 2.71. Remember that for pi, we also just keep two digits, 3.14, and 2.71 is enough for us for this course in most of the cases. But the important thing that comes up is that how and why on earth a mathematician in 17th century should think of a number which you cannot obviously compute, and how this number basically came to this world. Well, the person who found the number actually is not Euler. This is funny thing that happens all over the math. The person who first discovered this number is a Swiss mathematician called Jacob Bernoulli, and he found this in 1684, 17th century. But why such a number was important? Because it was all down to this problem. An account starts with $D and pays 100% per year. So we have an account. Each year we will get interest of 100%, and then we are interested in how much will the value of the account be if, well, we cannot say for sure just by given that the interest rate is 100%. What is important is that how often the interest will be credited. So if the interest will be credited, well, different cases. Let me just tell, well, what happens if it credited once a year, or maybe twice a year, and well, increase the number of these compound periods or intervals. First of all, why such a thing is important? It's very nice to see it here, because if at some point we started with $, if at some point interest is credited into the account, we from that the end of that period, we not only have $, in our account, but also $, plus the interest of that period. How this going to change the final result? Because from that point on, the interest will be calculated not only based on the original, the initial value of the account, but also the interest that already credited into the account. So from that point on, this is the value, and the interest will also consider for the value of the interest given at the end of that period. That's why it will change the value, the amount of money in the account at the end of this 1 year. Okay, the very simple case is that we start with 1 year. So during the year, nothing happens. At the end of the year, we have the initial value plus the interest, which is 100% of the original value. So this means that we will get, at the end of the year, we get double of that initial value. Well, if we get it twice a year, let me draw it a little bit longer here. So it will be 6 months here, and then the second 6 months. What will happen? The interest is 100% per year. So for each 6 months, we will have 50% the interest rate. So what does that mean? That means that if we start with the initial value D, at the end of the first 6 months, we not only have the D, the original, the initial value, but also the interest, which is half of the initial value. So it means that at the end of the first 6 months, we have D times 1 plus half. Well, if then we go into the second 6 months, now the D times 1 plus half is the initial value for the second 6 months. From this point on, we have D times 1 plus half, and then at the end of that second 6 months, we are going to have this initial value plus half of that, which is this number. Means what? Means that if I factor out D times 1 plus half, this will give me 1 plus half, and that gives me D1 plus half to the power 2. 1 plus half to the power 2, this is 1.5 squared, and that value is 2.25 times of D. And you see that right away, turning the 1 year period into 2 6 months periods will give us higher final value of the account. Well, similar computations can be done, and you will see that if for example 3 times this will be credited, the interest will be credited at the end of the year, we will have 1 plus 1/3 to the power 3. 4 times it will be d times 1 plus 1/4 to the power 4, and then this continues on. Well, for 2 times we had 2.25d. For ones we had just 2d. Here this number, I already have it somewhere, 2.370, repeat that, times d. You see it's getting bigger, 2.441d. Well, this continues a little bit, approximately this amount. And if you increase the number of these intervals in general, you see that n times a year, if the interest is credited into the account, the final amount will be d times 1 plus 1 over n to the power n. What Jacob Bernoulli was interested is called continuous compound interest. It means that let n be as big as you like, and when the compound intervals are small and small, so the small periods, so it means that more number of intervals. So when n grows very large, and when n grows very large, this 1 plus 1 over n to the power n approaches to the number 2.7182 and ... which now we call that number E. The Euler's number, sometimes you may see it's called Napier's constant. Okay, so that is what is E, and then the function, the exponential function with base E, in other words f of x equals e to the power x, is called the natural exponential function. It's the natural one. Well, as I said, this story is something very interesting, and what you need to remember from this video is what is E approximately, you know the value, and you know what is the natural exponential function.